Hello to everyone attending this seminar. Thank you for your participation. Today we have the great pleasure of having a talk by Dr. Filipe Terranova, who is a postdoc researcher of the Geophysics department of our institute. Filipe, thank you for accepting our invitation. And Filipe got his bachelor and master degrees in geophysics at IAG, right, Filipe? And later on, he moved to Nantes, to France, where he got his PhD at Nantes University in 2018. His areas of expertise are geomagnetism and hydrodynamics, and his research interests include geomagnetic fields, dynamics on various time scales, core mantle thermal interactions and dynamo properties, mechanisms of geomagnetic dipole moment variations, and also planetary magnetic fields. Today, Filipe is going to present the seminar Cooling Patterns in Rotating Thin Spherical Shells, Application to Ganymedes and Titan Buried Oceans. Questions can be asked to Filipe after his presentation. And if you are following this seminar on the YouTube channel, please write down your question in the chat. Before the seminar starts, I would like to ask everyone to please turn off your microphones and cameras. And Filipe, you can start whenever you are ready.
Hello everyone, thank you for the presentation. I will today present you some work that I've been doing the last 3 years, more or less. It's entire screen. Just wait me for share. So today I will present to you the cooling patterns in rotation thin spherical shells. It's missing the shells here. The first mistake already. And then I will show the applications to Ganymede and Titan subsurface ocean. I will explain better later. So basically, I will outline the presentation as follow. I will start by introduction. Then we're going to see some methods, basically the magnetodynamic equations, and then I will briefly discuss the results in Amit et al. 2020. That's a paper in Acros that I was part of. And then the paper that I'm preparing to send to Icarus in the next few weeks. I hope there is some few months that I'm saying that, but I hope that in a few weeks will be the case. So let's start with the introduction. So what I'm talking about here is about bird oceans. So when we went to the to be honest, when I start looking at the university, like when I was in the high school, like really at a young age, I was always like I was always looking forward to see the planets. Like when my first teacher talked about Pluto, when I first teacher about talk Jupiter, Saturn, I was saying, "Whoa, when will be a time that you go there?" And it was pretty sad when I discovered that they were so far away that it would be impossible to me to go there at any point in my life. I remember of being really sad about that. But this is not enough to sell. So when we want to go to the space and study the space, we want to sell better. We want to show that there is something there out there that people here in your planet will be interested about. And the thing is life. So the things that sells better is life. We're going to try to find life outside in the space. So bird oceans is one of the objects that can hold that, because these rich planetary boundaries in the solar system are considered to be ocean worlds, because they are like made of ice, but they have enough energy for maybe for liberation, maybe from gravitational tides, and they have enough energy, internal energy, to melt, and then they form this liquid water beneath their ice shells. So these are the bird oceans that we are interested in. Sorry. buried oceans are in the ice moons. So the first ice moon that I show here it's Europa, and then going to see the internal structure of Europa. There is a core, iron nickel, metallic core, and then there is a rock. Then there is the ice shell, and probably if there is some kind of ocean, it's beneath this ice shell. So this is the Europa system. And the Europa was kind of the first one to be discovered because of the Jupiter's magnetic field, and then this you use some induction of electrical currents to see that the values are only possible if you have some kind of liquid here. This also is done by theoretical models, thermal models. And also in Europe, in Europa, you don't have like an atmosphere. You can see the surface. And then when you have this photo, this is the photo of the surface of Europa. And then we see these are different colors, and basically these colors are more to indicate that these are probably some ice structures in the surface of Europa. And this is strong evidence for ocean, meaning why ocean? Because it's something that should probably come from below. This is a more this is one of the reasons because the Europa is going to receive JUICE. That's an upcoming mission, because they are really much interested to know if these things, how true is this, or how the extent of this is. This is just in a ice crust in the Connemara region of Jupiter, moon Europa. It's not like we don't know the the precise size of this. So when you go to Ganymede, there is a big problem to measure, because there you have an iron core. So if you have an iron core, basically it means that if you have enough to melt and then it's liquid, you're going to own a magnet field, and then you make more difficult to measure from using the electrical currents from Jupiter. But also we see that the interior is similar. You have the ice crust, and below this we probably have a melted liquid layer. So in Ganymede, to know that probably we had a buried ocean, we saw that there was the magnetic field from Ganymede causes aurora, and these auroras, they were kind of deflected from the precision degree that they should be if there was an ocean or if there was not an ocean. So this is really interesting that the magnetic field at the beginning was a problem to allow measurements was used after by scientists to, in matter of fact, to show that there is an ocean below Ganymede too. So Titan, I even left this big test because I don't want nobody to read this big test, because I just want to realize that every time that you see a planetary system that there is so many layers, it's probably wrong. I'm not saying that it's totally wrong, but in saying that we have so much troubles to solve all the dynamics from inner to outer boundary that we have to put a lot of layers. It's more or less when you are calculating an equation and then you have to put more and more and more variables to make something works. So basically, the state of Titan is that if you really look to the internal structure of Titan, we are pretty far away from know exactly. But by now, the models say that we probably have a silicate core, and then comes back to high pressure ice shell, and then we have a global surface ocean. So what's the most interesting about Titan? That we have both ice in both boundaries. So that's the difference from the others. And Titan is so difficult because they have an atmosphere, so you cannot see the surface, you cannot like have some idea from the surface. And then from Huygens, they left Huygens follow into Titan's atmospheres, and then here you are seeing is a photo just before the highest, I don't know how to pronounce that, sorry, fall into the ground. And then you can see that it's one of the photos that we have about from Titan. I don't see much, but it's kind of beautiful. So next we have Enceladus, also in the Saturn system. This one is pretty challenging because the hydrodynamic models that I use, for example, I cannot run anything that can run what Enceladus needs, because they need so much details, because there is a lot of diffusion happening here. I'm not too much in detail in Enceladus. But the thing that also interesting about the ice moon is there is a ice jet in the south hemisphere. That's intriguing. And this ice jet is kind of being used by the Saturn's rings as supplemental material. And the other big one, it's Minas. And this is intriguing because she's close to Saturn, so she should be having a lot of energy coming from tidal waves and stuff like that, because she's close to Saturn. So there's a lot of energy there in these two systems, but she doesn't have any like when you see a planetary body and you see like this kind of looks like a moon, you see it, so it's dead. It's the first thing that comes to your mind, because if you have anything like heat inside, the heat should be going out at some place, and then you see just this dead place here. Like in Earth, you see these plates that subducting. You see all this movement. All this movement means that there is something, like there is a source of energy inside the planet. And Minas, we expected to have that, but we don't see much. So inferred from geophysical measurements in theoretical models, also for sure from the information from surface. And we see that these systems, the Saturno and the Jupiter system, they have like these 3 moons. They have more moons for sure, but I'm here just talk about these 3 that we are most interested about. And these moons probably have like oceans. Minas, we think so because she should have a lot of things happening inside. Even if you don't see nothing outside, it's a mystery, but should have a lot of energy inside. And since she's ice, she should probably have also a buried ocean. So probably these 5 here are more related to this. And why we're going to talk about this, why we're going to be interested about this, because this is potentially habitable extraterrestrial environments. And let's just take a focal. So why I started work on this? People here for sure don't know me because I'm from geophysics, but exactly because in geophysics what I do is I work with the geomagnetism. I work with the Earth magnetic field and with the outer core, because the outer core is liquid, it's a fluid with iron, and this iron moves, and then there comes the Maxwell equations, and then I have a magnetic field, and this magnetic field is the magnetic field that we have here for the Earth. And so what's the geometry of this? The geometry that you have a layer. See, you can see like at the Earth, you see the outer core and the inner core here inside. And then there's outer core, inner core. Because the inner core is a solid, you start to have a geometry. And I studied a lot of this in the Earth. I studied a lot of when this geometry can concentrate some kind of flux, magnet flux in some positions. And I tried to see if these positions are persistent in time. So here, this was something that I brought from geomagnetism. But the single tangent effect is for every rotating fluid body between solid layers. So this is also what happens, for example, in Titan and all other ice moons. The difference from Earth to the ice moons, the outer core of the Earth is much more thicker than the oceans. The oceans are much more thinner. So the purpose of ALPHA was to study the effects of this thinner layer. So we are doing a really simple thing. Here, I just showed the example on the Earth, so geomagnetic flux patches. So, for example, the inner core and the outer core geometry form these axial columns in the just in the edge of the tangent cylinder. So this is something that we also expect that we see this in the Earth, and then just for the geometry. So also we should expect for the ice moons. So basically, the two things that we should take in mind here. The first one where I talked, that the icy moons, the ice buried oceans are much thinner than the Earth to comparison. And the difference too is that when we measure the cooling pattern of Titan, well, this means where is the heat is escaping more from. So when you go to the Earth and then you see the results for the Earth, you see that the escape of heat is much larger in the equator than in the poles. This is the effect of the axis of rotation, and the fact the rotation is really strong on Earth. So when you go to see Titan, for example, when we see Titan, we see that the heat flux escape, the escape of heat is larger in the polar region than that of the equatorial region. Sorry. And then that's what I try to fix. So we want something that's thinner, and then also we want something that's not cooling from the equator but cooling from the polar region. So let's go to the methods. This is the equations that we use. For sure, don't use all because we use not the MHD equations. We do just the HG equations, as a matter of fact. So everything that you see in magnetic field, you be going to zero. Basically, my PM here, you regulate that to take all that out. And these I don't include in the equations. So basically, my equations are a force balance, conservation of energy, and conservation of mass. And then if you want to see this in better, more detailed, so it's inertia, viscosity, Coriolis, Archimedes, convection. This is the forces that I take in account. And for the fluid transport, for the temperature transport, it's advection, thermochemical diffusion, and circular cooling and inner core freezing. So you saw this bunch of equations, and then you don't need to worry about, because when you're going to use the codes, you just need to know some control parameters and boundary conditions, and then they give it to you a complete solution of velocity, magnetic field, and temperature. The code that I used took more or less 12 years to be developed. So it's not something that we do ourselves. Like we use codes that are already done. It's free code, so you can use, but you need to use supercomputers because it's really high demanding. And so basically, when you go into do your numerical diagram simulations, you just give a list of values, and just here I'm doing I'm really being just to showing the four most used as the Ackermann, Rayleigh, Prandtl, the Prandtl magnetic, and the Prandtl. For us, they don't use the Prandtl magnetic, but basically, it's Ackermann number that talks about viscosity Coriolis. So how much its rotation making a work on your model. The second one is the Rayleigh. It's talking about how much convection, how much strong is your mounting, you, how much is the imposed force by your thermal force. And the other is about the fluid. So like we talked about, also for the ice moons, we need to really see the geometry, if there is something difference between outer core and the inner core, like the ratio between the two. So now I'm going to show the results. We did like rotation convection simulations in a thin spherical shell to study fluid dynamics in subsurface oceans in ice moons. So let's see this. This is the first part of the job of the job, matter of fact, because it's the project. It's a large project. It's the first one, and this first one uses homogeneous thermal inner boundary models. So what that means that in the inner boundary we imposed a constant temperature to regulate the convection of the simulation. So here's the case numbers. The second column are just the geometry. We tested just a little bit. We tested 0.7, meaning a more thicker, the more thinner. These are the values considered right by the literature. And then here is the strength. Weaker is this value, stronger is rotation. So the case 11 is the one with stronger rotation. And here, the strongest this number, strongest is the imposed convection by the hits, by the source, by the inner boundary source. So, like case 10, there is a strong inner boundary source, for example. And tells us how much you need to be at least bigger than 1 to say that you have a simulation that you won't die. And then just some grid parameters. Here's our more results, and then you see the Rayleigh number, and then you see the magnitude of the flow being really strong for for bigger Rayleighs. Sorry. And here below, I show snapshots. What are snapshots? Like the simulations that take long. The duration here are in advection times. It's not, but it's kind of 1 week, 2 weeks in supercomputers. So I think this is long. And then you have like these snapshots you have this simulation that go time by time. And then you can take these photos of how the simulation is at the time, the snapshot, or you can take all the simulations at the end and do an average. And then you have some results that are more trustworthy. So here are snapshots, and then is there more to show? So the zone average temperature, like we said, we impose a homogeneous inner temperature. So the temperature is, and then how she distributes because of the geometry. There is the vorticity, is more the flow, and then you see that these represent that we form the same columns that we saw the line there in the geomagnetic field models. I showed the examples, and then you see that they are close to the positions that the geometry of the tangent cylinder they impose. Like here, you can see even better. See like the geometry impose that you cannot, that you are more, your convection cell is more located to this equatorial region. Because in Earth you can be here, so you have much more space here. The equatorial cooling should be even more efficient. And these two below are the heat flux across the outer boundary for two different longitudes. So you see that this is the flow, this is the heat flux, the temperature, the difference of the temperature at the top of the shell, the outer boundary. And then we see these strong colors at the equatorial position. This is a good example of equatorial cooling, something really close to what happens in Earth. Here show other examples for other coolings. For intermediate cooling, you see that you have strong equatorial cooling, strong polar cooling, and then you have this low here. And it's interesting because it's really at the tangent cylinder. So the tangent cylinder here is doing a different effect. It's breaking here the cooling, but doesn't affect the polar. Like here you see the equatorial cooling and then breaks at the tangent cylinder and then still goes down to the pole. So it's almost no heating. And here's the one that starts to grow up from the tangent cylinder until the pole. It's the polar cooling, something that's something that we are looking for because of the results from data from Titan. So here basically I'm showing the results from the case before. Like if you remember when the case 11 is told that the rotation was the most, where rotation was most strong. And then you see that they gives also the strong equatorial case. So basically, if you have a lot of rotation, you probably have your equatorial cooling exactly as we expected from the Earth, for example. And also we see that when you have like strong, I do not remember to, but case 10, I'm telling you now, you should believe, has a really strong value of Rayleigh. So meaning the main convection that imposed, saying that my energy from the inner boundary is telling you to be strong, and then he's not so efficient. You see that the values are much smaller than for the equatorial, but it manages to have polar. And the interesting part is that the polar cooling really needs that to have the strong plume, let's say this. But it's not so true because here I'm looking just for the table. But when a combination of the both works better to explain everything, and then I show you how. But the main message from here is that the equatorial cooling here really shows more efficiency than the polar cooling. Here I show the images from before. Now you're going to see them stacked to show better in collage to the effects. And then we see how case 11 with the equatorial that has a really strong equatorial cooling. See the peak here. And you see how it works for the polar cooling. And after what we did, we tried to see what was the regime for buried, the dynamic regime for buried oceans. So what's the importance? It's rotation, it's convection. And then I told you it was probably a mix of both. And then when it's a mix of both, we are talking about Rossby numbers. And here there is a bunch of there is, matter of fact, two Husby numbers for different quantities that we calculated. So the mean value of the flux, of the heat flux. Here is the amplitude, like how much this flow is different how much is the lateral heterogeneity of the flux, of the heat flux. And the last one, the one that we are more interested in, is the one that we showed before. I showed before in the table, that tells you if you are equatorial cooling or polar cooling, and then you see that there is really a difference between the two regimes. That the polar cooling, like the equatorial cooling, it is really low values of Cosby numbers. So it was really cool because we saw a value that was previously also calculated by Sunderland in a big paper for him. Next, we saw also, this is a diagram from Gastin, 2016. And here there is a lot, here we show that flows really sorry. Here we show that all models close to rapid rotation. Sorry, there is a lot of noise here. So, sorry, I was saying is that the equatorial prevail when the models are close to rapid rotation regime, whereas the polar cooling emerges when the models are close to the non-rotation regime. In both cases with the transitional regime. So this means that we tested the transitional regime. There is a lot of more parameter regimes to be tested, you see here. So this is tested just in the transitional regime. But when they are close to the rapid rotation regime, we have the equatorial cooling as expected, because half Earth is here, too close to rapid regime. And then when we go to non-rotating, we are more close to polar cooling. So this is basically telling us what to expect. So this is trying to give a clue if we are expecting to have a rapid rotating Titan. We should not. Why? Because, or at least the rotation effects should be not so well sensed, because we have a polar cooling. So now just the conclusions of this work, and then if you all want to talk about it more, and I can also send a copy. This is a paper that was published last year. So basically we show that we managed to have a polar cooling, and then this result is really related to the Rossby number, so related to the level of inertia. And then we saw the polar cooling scenario. It's an algorithmic inference from the heat flux at the top of Titan's ocean. So now the second part, this is the part that starts what I'm doing now. I hope to submit soon. So basically what we did was the same thing, but with one specific difference. We imposed, like in the first part of the presentation, I showed models with homogeneous boundary condition. To be more precise, with constant temperature. And here we do two paths. We use heat flux, not temperature, and we don't do fixed, not homogeneous in the case. We do heterogeneous. We take this from simulations in the high pressure ice mantles. And then there are several simulations, several situations that are possible for the inner boundary. And then we took one of them. This is a photo of how it looks, how is not or not our inner boundary heat flux. And below is the model and then the parameters that we use it. So we use a lot of parameters, and there is a new column that the other paper did not have, because now we're also imposing how much is the heterogeneity of this. So how much the strong blue is far from the strong blue. Well, from the strong red is far from the strong blue. Sorry. So basically, imagine how heterogeneity, how strong is the heterogeneity that we impose. So the first test is Rayleigh. Rayleigh, we remember, is the main convection, the strength of the main convection. And then when we impose strong convection, what happens? I think it's not a surprise to us. The columns that we expecting to have, you see, dying the tangent cylinder, they get thinner and then hard to see. And then when we cruise just the amplitude, we don't see much difference, to be honest. It's kind of disappointing because this is something new that we impose for this part of the paper, but the difference between these two are not so. We see kind of more structures in the polar region, but could even be just not the model is not converging enough. But one thing that's more robust is to see that the increasing of the main convection really takes these equatorial columns and making them really thinner. This is a real result. Now, when we look, this is out for equatorial cooling. You see here it's more strong in the equator. Now for the polar cooling, when you increase the Rayleigh, the same thing happens. You see, still the cooling here is strong. Then here, believe me, I calculate that, and not by much for sure. And this stronger cooling, this stronger polar cooling, it still has some kind of these axial columns. But when you increase the main convection, they disappear. And again, when you increase the amplitude of the anomaly that imposed for the inner boundary, it's not much difference in the results, fortunately, again. And here, just to show you the difference, so it's just polar and equatorial view of the boundary heat flux anomalies. So characterized by equatorial cooling. So here we really see the strong red, meaning I'm escaping more heat here, and then no heat in the polar region. The dashed lines, these dashed lines, sorry, denote the tangent cylinder. And when you see the polar, you see already these columns disappear, and then just this more small scale. So it's a different kind of dynamics, and there is more small scales, but it's much more. You see that's more strong in the polar than the equator. So something that we expect to Titan. Here I show the latitude dependence of the time average of the boundary heat flux patterns. Is the figures from before, just to show in co-latitude. And then you see that we have these positive anomalies, seeing that we have really strong equatorial cooling, but there is a really drop in the TC. For the polar cooling, you see that the differences are not so strong. And more than that, the tangent cylinder is not so well seen. Still some, but not like this, well marked. So this is the dynamical region. So now we're talking about not heat fluxes, but about flow. And here we see that the flow shows really the columns that we see outside the tangent cylinder. There, this is similar to the Earth. So back to the Earth and see the now a slice and see strong. The strong is close to the tangent cylinder. And then here, when you see for the polar, you see that the flow is more strong at the polar regions. And now, like in the first part of the presentation, I showed that we also try to see what the relation through the Rossby numbers. This one also takes into account the amplitude of the heat flux of the inner boundary heterogeneity, and this one doesn't. As this one doesn't, we can also compare to results of the first part of the presentation in Yamich et al. 2020, that they are the red ones, and then we see that we have some kind of agreement that from some part of like there is a limit of value of inertia where you have polar cooling and you have equatorial cooling. This was pretty cool because we, even if you use some difference, because he used fixed temperature, I used heat flux, I used heterogeneous heat flux, but the main result of this paper, we still have the same result. So this was really a good thing. Basically saying that inertia regulates if you have a polar or equatorial cooling. And the last thing that we are trying to see is the impact of the boundary heterogeneity. Basically, all the scope of my part of the job, of the project, is to see if any kind of information that I can take from from the surface, you tell something for me about the internal part of Titan. So meaning that if I can measure the temperature of the top of the ocean, maybe I can transmit the information about the bottom of the ocean, and then I have something more. Or the opposite. So one thing that we saw is that the inner boundary, you see this in the figure, there are the values here if you don't see it so well. Basically see that the polar regions have much strong, that even if the polar have much less, like you need to have much more strong source of heat to have a polar cooling than to have equatorial cooling that basically needs more equatorial than more rotation than convection. So when you see the outer boundary, and the outer boundary shows some similarity to the inner boundary, you see that basically there is some kind of information that is transmitted. And for us, the cool result is that the information was strong for the polar cooling. So meaning even if the polar cooling is more difficult to have in terms of simulations, in terms of what kind of regime that you have, the polar cooling could also, it's more reliable to transmit the information from the sea floor to from the sea bottom to the sea floor. And that's it. This last part of the presentation was more about a paper that I'm still working with. So if you have questions about all that, you can ask me. Hope you like it.
Thank you, Filipe, for the presentation, for the talk. Now, let's move on to the questions. And I think
How I do? Okay.
I have here the name of, I think Maria can start the questions. Please, Maria, go ahead.
Yes, sure. Thank you for your presentation, Felipe. I have a very well, for me, simple question, because you mentioned about the aurora in Ganymede. Can you comment how this proceeds? Because I only think about the aurora here in Earth, but how is this also due to the solar winds?
I don't know in detail, because this is really because Ganymede has a dynamo that works different from the Earth. Like it extracts heats different than the Earth. So basically, don't have any information about that. So basically, now we are in the point of making the models to understand how it works. You have no information. So every information that you have about the auroras is basically inference. So you measure the data and then that's it. Why this happens and why it happens like this, we don't know. Just saw that because the aurora should be at 6 degrees, and because why should it be at 6 degree, and I don't know. But I know that the deviation to 2 degrees is because of the ocean, something like that. So this is that they use. But why there is this deviation? Why is this aurora? The aurora is basically because you have the geomagnetic field, and the geomagnetic field protects from the particles that come from the atmosphere, and then probably this region is weaker. There's a weaker region, like where the particles are more probably to enter than not. In Earth, we have something similar too. Like in Earth, we have something similar, like we see.
Yes. Okay, thank you.
I have one question. In your model, so you have this profile for the temperature of the inner boundary, and in the beginning, you showed a model where you put a uniform temperature as the boundary value, and then you also tested another model where you regulated the heat flux in this inner boundary, right? Is it so?
Yeah.
But it's so.
It's problematic for sure.
Right.
Because we did 2 steps.
Right.
Because the first work was just fix a temperature, and then I should go to fix a temperature. Then I should go to fix it heat flux, and then I should go to heterogeneous heat flux. You know, because I did like 2 steps in one. But you can keep asking. Sorry.
So anyway, this process of cooling, it's cooling the inner part of the moon. What's the source of the energy of this inner part of the moon?
I hope this
friction.
No, I think Titan is heat tides. So basically the attraction. Basically I think Titan for sure is this one, because because the results that I have, I'm sure that come from a guy that is specialist in gravitational fields. So it's basically using this to this. The luckiest thing is that these big planets are around. So these big planets give a lot of information, because we don't have like money to go directly to the moons. Maybe now Europa we're going to see more closely because of the oceans.
Right. I have other question, but let's first move on to Betty, and then I come back. Thank you. Betty, please go ahead.
Oh, hi, Filipe. A very interesting talk. Thanks. I have a couple of questions. I have 2 questions. Because you have a model that essentially is very similar to the models, or the tools that you use are essentially very similar to the tools that we use to describe stellar dynamo or solar dynamo, right? And you have also this dependence of the, let's say, the cooling flow activity with the Rossby number. On the other hand, in the dynamo, we have this dependence of the magnetic growth or the magnetic activity with the Rossby number. So my question is, have you have you had the chance to analyze the influence of the magnetic fields in the evolution of these flows? In of your cooling or heating flows in these systems, in these objects. And also, this is kind of related to the question of the source of the energy, right? That is implied in the dynamical evolution of these systems. So this is my first question. And the other one is the Prandtl number that you of course, you have viscosity and you have resistivity as well, because the magnetic fields are present there, and you have explicit resistivity in your equations. So my question is, what is the Prandtl number that you employed? Just because I'm trying, to compare your simulations with what I know from solar dynamo simulations. I mean, with the
magnet field, we are far away of using it, because now we are just using the hydrodynamics, and the
so
thing
you did not have a B different from zero. So I
No.
got, because when I entered, I thought that you were employing the equations with the magnetic
I just use the same slide. I should be more careful about that, but I use
but anyways, the
hydrodynamics.
question about the Rossby number, do you have an idea on this, and how magnetic fields could influence your results?
I think really low. I think it will not change much, because we don't know, like this answer should answer the both things that you asked it, because we don't know the properties of the fluid so well. So when the Prandtl that we use is not, it's kind of a gas. So it's kind of a gas, and then we don't pay much attention to this, because
Prandtl number is infinite then, right?
No, this is my magnetic Prandtl number.
No, because the Prandtl number is the resistivity over is viscosity over resistivity, magnetic resistivity, right?
No, the magnetic Prandtl number, but there is two: the magnetic Prandtl number and the Prandtl number. The Prandtl number is just about the fluid, like how much viscosity and advection fights between each other.
Right.
And then as I don't have magnetic, my concentration in the fluid properties, like in Earth, use both the magnetic properties of the fluid as well as the viscosity properties of the fluid.
And about the hydro, what is the value that you are using for the Prandtl number?
The hydro just use the viscosity properties of the fluid that they are not so well constrained. And they don't constrain so well. So the simulations are more or less to have idea if in a thin shell, how inner boundary could influence the outer boundary. So it's really simple, and this at the same time when you're going to run this, it's a nightmare.
Right.
The convergence of these simulations it's a nightmare. So to include the magnetic field, it's beyond my imagination. In the future, for sure. And it could influence a lot. I probably not, because the PM that you are talking about, the magnetic Prandtl number, it should be really big. So
even if it's big, it doesn't mean that the dynamical effects of the magnetic fields are not important. They can be rather important, actually, for very high values. It can be very important. But I understand that this is beyond the scope of your work.
No, it's the scope.
But it's interesting because this correlation with the Rossby number is also a key issue for the magnetic activity, and therefore they might be connected somehow. But yes, very, very, very interesting work anyways.
Thank you.
I have Two more questions. So from your simulations, besides the heat pattern, the heat flux maps, you also get the temperature, the map of the temperature in this buried ocean, right?
Yeah, because I impose the temperature and then I see how the temperature the evolution is the model that does.
Right. What's the average value of the temperatures the close to the poles and close to the equator?
No, we impose the same. It's a
Oh,
isotherm. For the first
okay.
one, it's a isotherm.
Isotherm in the internal boundary.
Yeah, and then
But, but in the
the
fluids?
geometry does the thing that gives more heat to the just the thing that you have a rotation body, and then they always want to make the heat to escape in the equator. But if you have some kind of strong convection that can broke these these columns that should be created by the helicity, you see, the rotation creates these columns of helicity. But if you have a convection that's so strong that break these columns, you have the polar cooling being more important than the equatorial cooling. But this is totally no efficiency. That's the bad part of that we saw it. Like
Right.
the why he's doing the polar cooling. So probably it's still say you don't answer this. Why is still doing the polar cooling? But we see that there is a parameter regime using these simulations that show that there is that's possible to do a polar cooling. That this polar cooling needs to have strong inertia happening. So that means that they need really to the flow to be really not so chaotic. No, it's to be chaotic, but it should be more is exactly the opposite. To be more chaotic, like inertia gives more chaotic, more chaos.
It is a turbulent convection, isn't that so? Sorry.
Yeah.
Right. And to so you have your models for the pattern of the heat flux. Is it possible? Okay, it also disturbs the pattern of probably convection, the circulation pattern. So I guess this influences. How can it be measured by the spacecrafts or by the sondas, or is it possible it has effects on the magnetic field, or?
So, if I'm not mistaken, the magnetic field of Titan should be considered. I don't know if even it's considered because like
Right.
Ganymede there is a dynamo inside.
Right.
If we have a magnetic field comes from the ocean with some iron inside, some you see, like ice ocean movement. So this movement should not be so strong because we need a lot of movement. So here we are to see if there is convection based just in temperature. If you want to have a magnet field, you have to have enough convection to be strong enough to. I don't even remember why. Like you have a dynamo, but you'll be weak.
Right. Because I'm thinking of the inverse problem. If you can extract some observational information to
No, but
infer some
this
inertia or structure information from the
but this is the goal.
moons.
This is the goal, but it's so far away now. Like we are still in the
Right.
models and theoretical models. And then this is more or less for each planetary body. If you really look, everyone is trying to take like some information that we have, but this is changing in 15 years, like 50 years, but at least like because now we're going to be juice, and then 20 years after something else, and then
Right.
it takes long. It's difficult because of this, because you cannot like say, oh, let's give this to a PhD student, say like, oh, maybe in 3 years, maybe we have data about something, use an instrument that maybe be someone. So it's I work in a planetology lab, and sometimes we have just these PhD students that start a PhD to do the seismolog that goes to Mars to measure, and then next week they just change something and then it's dead. The PhD of the guy is dead. So it's so sad. So they stopped doing that. So it's really hard to advance because it's really like old people old people. Like I went to the natural dynamos conference in Republika Czech. Like there was so much old people. Like man, and then there is no there is it's hard to make people want to study stuff. Like I was in Earth and I started to work on this, and there is not much people work on this, to be honest. Like just running hydrodynamic models for this planetary body. There is one guy in France now that is doing a dynamo model exclusively to show how Ganymede field works. So there is people working, but it's like one guy doing this, one guy doing this. It's not like in Earth. There is a lot of people working together in advancing. So this part of hydrodynamics of planetary bodies, it's one guy, Chris Jones from England, that have some students that work with him, and that's it.
Right.
There's Schubert, that's already tried.
And what would be the most important observational data that you can get from the, let's say, from these moons to maybe to improve your model in the future, or to talk with your...
For example, the polar cooling. If they could tell the difference between the polar and the equatorial cooling, like the ratio that we have there, they give us one number. Like imagine that all we want is one number, and then we're going to look for this number forever. Like in Earth, when we see the induction equation from the Maxwell equations, we see the Reynolds magnetic numbers equals to 100. So this is what everyone that was doing numerical dynamo simulations for the Earth was looking for. I'm looking for the not 100, 1,000, 1,000. I want this value, When my model got close to this value, I said, okay, now I have some model that it's good enough. So for the ice moons, we don't have even this value.
Right.
To say, okay, my simulation is close enough. Yet.
Right. Yes.
Like someone can come with a crazy thing, see the aurora boreal with flags in the moon and then flags in the sun, and then I don't know, astronomy fix. This is from you guys, the astronomy. You always say, oh my god, how you know that? And then you say some magic, and I say, oh my god. So no magic.
Okay.
Yeah. But I am looking for it. If you guys give me some, okay, look, this is the value. I'm telling you, this is the ratio between the heat flux, like how much polar cooling. And say, whoa, and then I tell you, if you tell me this, means that your dynamics is restricted to these kind of things. The maximum things that I can do is this: restrict the mind of the scientist. Say, okay, this is the maximum that you can do. The models tell that you cannot like explode something here, or say that you cannot have polar cooling with axial columns in the equatorial. No, this is not possible. You have to broken this. So I'm telling you this. If you have polar cooling, you have this. But if you tell me, oh, I measure wrong, it's not called polar cooling anymore, it's equatorial cooling, and I need to go back there and then try to see what's it's basically it's a nice change, like between from data and model. This is the why I like most to do this in Earth, and I'm doing also for the ice moons. Basically trying to explain data with models.
Right. Thank you very much, Filipe. We'd like to thank you again for this talk. It's an interesting topic, and also very hard. I know the simulations are really hard to prepare, to control, and to run. It's a lot of work also to extract information from the simulation.
Yeah. They come in binary files.
Yeah,
0 and 1.
Yeah, and to make the analysis, it's very a lot of work. Okay, thank you again for sharing your work. Thank you, Filipe. Thank you for everyone participating in Google Meet and YouTube. And now we see each other in August.
Thank you for the invitation.
You're welcome. Bye-bye. Appreciate
Bye-bye.
Podemos fechar a transmissão.